Perl script that I wrote for looking at IP datagram and IP fragment sizes. I've got a capture file here, packets.pcap. It's got 160,000 packets in it, and we launch the script. Like that. This is just some header information up here. This line is going to print a red dot on the screen. These are the X and Y coordinates of the dot. This line will print an orange dot on the screen. This line will print a yellow line on the screen. There's the X and Y coordinates of one end of the line, and there's the X and Y coordinates of the other end. Dead simple syntax here. That is the syntax for xplot, which is a super fast and super powerful visualization tool. So if I send that same data into xplot, it takes a little bit. The fragmentation reassembly lookback buffer that I implemented is pretty stupid and doesn't run very fast. Okay, here's the result. Put that in the window there, make it a little bigger. So we have here about 20 minutes of capture data. The time scale down here shows us 20 minutes. The vertical scale is IP fragment size. That is not the size of the IP packets, but the size of fragments. If it happens that a packet is delivered whole, then those two values are the same, but otherwise this is just the size of individual fragments. Each green dot is represents an unfragmented packet. So if we look at the top line here, we got several packets that were 1,496 bytes. Those are the biggest ones that were delivered unfragmented. At the other end of the scale, we've got a whole bunch here that are 88 bytes. So those are the smallest ones that were delivered. You can see easily that there was 5 minutes of relatively a lot of activity, and then about 10 minutes of quiet, and then data rates picked back up again. This sort of diagonal band here is kind of interesting. I don't know what was going on there, but something was getting bigger or faster over time. It's sort of interesting. A lot of horizontal banding. Many packets here were exactly 1,288 bytes. Many were 408. I don't know if that's too meaningful, but it's sort of interesting to see those stripes. This big yellow band through the middle here is the fragments that I received during this capture. Each time an IP fragment rolls in, rather than plotting it in green, I will plot the 0 offset fragment with an orange dot, and then I will plot subsequent fragments with yellow dots, and I will connect the yellow dot fragments back to the frame that represents the prior data in that IP packet. I only have samples here of packets that were cut into two pieces, two fragments. If there had been three, this would be, there'd be 3 points on the screen here, and it would be a continuous line starting with orange and then through all of the subsequent fragments, connecting them all together. There's another case here. Well, interesting to note that in all of these cases, if I look at one close again, you can see the 0 offset, that's the orange dot, arrives first. That's around 810 bytes. And then after that comes the smaller packet, the later fragment, that's 750. So that was the pattern throughout. These guys that were fragmented were around 1,560 bytes altogether. Well, no headers, so 1,540, I guess. The 800 byte fragment was first, and the 750 was the subsequent one, both in terms of IP data offset and in terms of time of arrival for most of them. But there were a bunch where See this red dot here? There were a bunch of cases where it went the other way, where the non-zero offset, or the subsequent data fragment, that's this one, arrived before the first part of the IP packet, which is this guy up here. I didn't draw a line to connect those because I'm lazy, apparently. That would have been another bit of logic to implement that I just didn't do, and in fact I didn't even know to expect at the time. This is the order that a PIX would drop, and that Linux used to send things. You know, packet reordering happens on the internet. That's not a big deal, and you know, a couple things coming out of order shouldn't be something to get excited about. But when data rates were high, let's see here, if I can just grab a few seconds. Here's 2 seconds on screen right now, and there's, you know, 1, 2, 3, 4 of these guys out of order. There are some cases where, or some places in the capture, where it's even noisier than that. Here's a 1 second interval. How many is in that? There's one, there's one. So in this 1 second, 1, 2, 3, 4, 5, 6, 7, 8, 9. So at least 9 cases of reordering in 1 second here. That's kind of a lot. I look at TCP data a lot, and TCP data, it's really easy to pick out reordering. And even across the internet, you know, the loss is sometimes terrible, but reordering doesn't usually happen quite like this. So I don't know what's going on with this particular set of links, but there's a lot of stuff coming in backwards ordered. So that was kind of interesting. I banged the script together just because I wanted to visualize some of this stuff for this particular packet capture, because it looked like it might be interesting based on what I was seeing with my eyeballs and Wireshark. In the end, this didn't turn out to be too interesting. The problem I was trying to solve did not lie in this visualization of the IP packet sizes or fragment sizes, but that still produced some interesting data and pretty colors to look at. And maybe one day this will be useful when I feed some other data to it. Maybe also someone will download this script and do something else with it, and do some other stuff with xplot and the perl pcap libraries. And if that happens, I hope to share.